Welcome back. In the previous lecture, we have discussed on MOSFET, that is metal oxide semiconductor field effect transistor. This lecture, we will focus on another semiconductor device, that is the IGBT, known as Insulated Gate Bipolar Transistor. We will see its structure and characteristic. So the outline goes like this, where we are going to discuss the introduction of IGBT. We will discuss what is the structure and its symbol, the basic operation, the equivalent circuit, what are its characteristics, the switching characteristic, types and applications, advantage and limitations, the design considerations, and compare it with the other power semiconductor devices, and then we will conclude with the summary. So IGBT basically means it is insulated gate bipolar transistor. It is a hybrid power semiconductor device. Why the name hybrid is given? Because it combines the best feature of the MOSFET and IGBT. We have seen that the MOSFET is easy to drive and has fast switching, whereas BJT has low voltage drop and high current capability. So the best features of these two devices are combined in a hybrid mode to get the IGBT. IGBT has three terminals. Those are gate, collector and emitter, and it is also a voltage control device like the MOSFET. It is used in medium to high power applications. So the key point to be remembered is IGBT, which is a combination of MOSFET input characteristic and BJT output characteristic, and that makes the IGBT the best one in the power semiconductor devices because it combines the advantage of MOSFET and BJT. Why basically do we need the IGBT? Because there are certain device limitations in terms of MOSFET, BJT and thyristors. Thyristors we have not covered yet. We will discuss in the coming lecture. MOSFET are good for low voltage only. So when the voltage is more high, then MOSFETs are not preferable. The BJT need complex base drive circuit, so they are limited because of the base drive circuits. The thyristor cannot turn off easily. So these limitations of MOSFET, BJT and thyristor has necessitated the invention of IGBT. IGBT has a solution that it is for high voltage capability around the range of 600 volt to 6.5 kilovolt. It has a simple gate drive circuit similar to the MOSFET, and it has the high current capability up to the kiloampere range. It can be fully controlled both in the on state as well as off state. Some of the major applications of IGBT are it is used in the motor drive, in the UPS system, the welding machine, electric vehicle and solar inverters. Let us see the structure of IGBT. The basic structure of IGBT is 4-layer semiconductor device. So you have a PNPN mode. Here you can see the N-channel IGBT cross-section where it is having in the mode of PNPN. The three terminals you have, which is the emitter, collector and the gate, and the gate is isolated by thin oxide layer. So you will be having insulating layer of metal oxide, which is silicon dioxide, and that will be isolating the gate. It is similar to the MOSFET gate structure. So we have seen the MOSFET. So MOSFET and IGBT are similar in terms of its gate structure. It is a vertical power flow design, and some of the key features are the gate will be controlling the electron flow, channel formation will be there under gate, hole injection will be there from the collector, and high current density capability is there for the IGBT. IGBT again are basically of two types in terms of symbols. It is N-channel and P-channel IGBT. So this arrowhead differs in case of N-channel and P-channel. So the most common type is basically the N-channel IGBT. The arrow shows the direction of the current. The gate will be controlling the device. In P-channel, which is less commonly used, reverse current direction will be there compared to N-channel, and it has the same operating principle. We have to remember that the focus will be on N-channel IGBT as they are most widely used. Let us see the working principle of IGBT. So the turn on process, simply if we want to explain it, you apply the positive voltage to the gate. So you can see here there is a source which is connected in the gate, where the gate emitter voltage has to be more than the threshold voltage for the current to flow. So it will create the electron channel similar to the MOSFET. This electron will flow from the emitter to the drift region, and the holes will be injected from the collector. The device will be turned on. Then in the turn off process, you have to remove the gate voltage. So the gate voltage will be less than the threshold voltage. The electron channel will disappear and the stored holes must be removed. Then only the device will turn off. So the key concept is the gate voltage controls the electron flow, which controls the hole injection. So it is the gate which is basically controlling all the electron flow in the IGBT. What makes the IGBT to be special in terms of the conductivity modulation? So what do you mean by conductivity modulation? When holes which are from the collector entering the drift region, they increase the conductivity significantly. So we know the charge carriers in terms of electrons and holes. So here we are talking about the holes. These holes will be coming from the collector and they will enter the drift region, and hence the conductivity will increase significantly. So some of the benefits, it will have low on-state voltage drop, it will have high current handling capability, and it is better than MOSFET in terms of high current. So when we compare with the MOSFET, the current is high in case of IGBT. The trade-off is for the slower switching due to the stored charge, and the turn-off time is usually longer than the MOSFET. So these are the limitations as compared to the MOSFET. If we try to bring the analogy, think of it like adding salt to water, that will increase the conductivity. So these holes which is coming from the collector entering the drift region to increase the conductivity can be thought of analogy where you are adding basically the salt to the water, that is increasing the conductivity. You have to remember that the lower value of collector to emitter saturation, but slower switching will be there in case of the IGBT as compared to the MOSFET. IGBT equivalent circuit, if we think of, it can be made up of MOSFET plus diode, or it can be made up MOSFET plus BJT. MOSFET plus diode is basically the simple model, and accurate model if you want to go, then we have to go with the MOSFET plus BJT. So here is the structure which is shown. So you will be seeing here, this is the MOSFET and this is the diode. Together it is combined to form the IGBT equivalent circuit. Here you have the MOSFET and the BJT. Together it gives more accurate model. So why it is a simple model, MOSFET plus diode? Because it is easy to understand, it is good for basic analysis, and it shows the unidirectional conduction. But if we talk about the accurate model in terms of BJT plus MOSFET, it is more accurate in terms of calculations, which shows current amplification, and MOSFET will derive the BJT base. We have to note that always use MOSFET plus BJT model when you prefer for circuit analysis and calculation, because it will be simpler and easy to understand from academics. What is parasitic thyristor? The important concept. Let us see the problem. So there is a 4-layer structure that can form a thyristor. We will discuss the thyristor in very detail. Here we will be coming with the concept of parasitic thyristor. So it is basically the 4-layer structure, and if activated, it can cause a phenomena which is known as latch-up. Here the gate is losing the control and the device may be damaged. So this is a disadvantage of the principle of formation of parasitic thyristor, where the latch-up phenomena take place and the gate is losing the control, so the device may get damaged. Here you can see the parasitic thyristor in IGBT. So this is your MOSFET and the BJTs are connected here. So these result in the formation of parasitic thyristor. How do you prevent it? So keep the emitter resistance low. So in the IGBT, if you keep the resistance of the emitter low, it can be prevented. You need to have proper device layout, and we need to operate the device in the safe operating area and use appropriate gate drive circuit. Note here, always mention parasitic thyristor as a limitation of IGBT and its prevention method. So when we talk about the IGBT, the parasitic thyristor is one of the major limitation of IGBT. Let us discuss the transfer characteristic. So the key parameters that will be involved is basically the threshold voltage, which is in the range of 3 to 6 volt typically, and the transconductance phenomena GM will control the current gain, and it is similar to the MOSFET transfer current. So this is basically the gate emitter voltage and the collector current, and this is the threshold voltage after which the IGBT start conducting. So that is similar to the MOSFET. Temperature plays a very important role because the threshold voltage will decrease when the temperature increases and the current will increase with respect to temperature. So it is important when we go for the parallel operation. The design point is choose the gate voltage 2 to 3 times higher than the threshold voltage for reliable operation. So whatever the gate voltage we have to choose, it should be 2 to 3 times higher as compared to the threshold voltage. Then only we will get the reliable operation. Output characteristic, when we talk about, then we are seeing the collector to emitter voltage with respect to the collector current, and we have seen the active region of operation in MOSFET, which is in the forward characteristic, and the reverse characteristic there will be leakage current flowing. So forward blocking capability has to be there. No reverse blocking should be there in case of which will be needing the anti-parallel diode. Saturation region operation will be there, and the collector to emitter saturation voltage typically has a maximum value of 3 volt up to 1.5 to 3 volt. So when we do the comparison, if the collector to emitter saturation voltage is lower in case of IGBT than in case of MOSFET, then it will have high current. Higher collector to emitter saturation voltage will be there in IGBT than in BJT. So compare the IGBT with BJT and MOSFET. So you are basically getting lower collector to emitter voltage saturation than MOSFET, higher collector to emitter saturation voltage than BJT. The shape of the characteristic curve is similar when we talk about BJT or MOSFET. IGBT switching behavior, what is the key difference from MOSFET is IGBT has tail current during the turn off. So due to the stored minority carriers. Now you will be having the minority carriers. These minority carriers will be creating a problem for turning off, and that will be resulting in the tail current. The turn on process is similar as like the MOSFET, and the gate capacitance will be charging and the current will rise quickly and the voltage will fall. So this is similar what we have discussed in MOSFET. The turning off process here is the gate capacitance has to discharge, current will fall in 2 stages, and there will be small tail current which will be slowly decaying, and this will be limiting the switching frequency. So here you can see the IGBT switching waveform where you have the small amount of tail current, and that tail current is basically resulting in slow decaying of the IGBT characteristic. And the most important point is the tail current is the main limitation in high frequency application. So if IGBT is used for high frequency application, obviously the current will not decay due to the tail current, and that will be one of the major limitation of the IGBT switcher. There is important gate drive requirement. So gate drive specifications. So IGBT will need proper gate drive circuit for the reliable operation. The voltage requirement is the turn on voltage has to be from 12 volt to 15 volt. Turn off voltage should be minus 5 volt to minus 15 volt. When you require faster turn off, maximum rating is plus minus 20 volt typically. So these are the voltage requirement for the gate to turn on and turn off. Current requirement is when we have the peak current, it will be in few amperes, and low source impedance is preferred. Gate resistor will be there for controlling the switching speed. So resistor which is connected in the gate will be controlling the switching speed. Some of the protection devices we will be using in the gate. So linear diode will be connected across the gate emitter. Gate resistor will be used for dV by dt immunity, and there will be isolated power supply. So the typical values that we use, gate to emitter voltage 15 volt in the on state, minus 8 volt in the off state, and the resistor of the gate we use around 10 to 47 ohms. So these are the design parameters for the proper gate drive circuit. What are the types of IGBT? So two main types we will be taking, and this classification is based on the internal structure and performance. So one is basically the fast IGBT and second one is basically the low loss IGBT. So when we say fast, it is lower switching losses, higher switching frequency greater than 20 kilohertz, and has slightly higher collector to emitter saturation voltage. These are basically used in high frequency converters. Low loss IGBT has lower collector to emitter saturation voltage, higher conduction efficiency, slower switching, and used in low frequency application. So for high frequency converters, you go with the fast IGBT. Low frequency application, you go with low loss IGBT. So if you see the fast IGBT application, which is in switch mode power supply, motor drives, and induction heating. If you see the low loss IGBT application, traction drives, UPS system, and large motor drives. So what choose the selection criterion? Choose based on switching frequency and power loss. So these are the two important phenomena that we'll be using to choose what type of IGBT is used. Some of the major applications of IGBT in industrial, renewable energy, or transportation also we are using it. So there will be all sort of application like motor drives, variable frequency drive, uninterrupted power supplies, which is the UPS, welding equipment, induction heating, solar inverter, wind power converter, energy storage system, electric vehicles, ship traction, ship propulsion. So many applications are there where we use the IGBT. So here the power range lies between kilowatt to megawatt. The voltage will be 600 volt to 6.5 kilowatt. So this voltage is very, very high. If you can see frequency up to 100 kilowatts, we can use it. Now IGBT is preferred because it is a good compromise between the switching speed, voltage rating, and drive simplicity. So these characteristic of IGBT makes it to be preferable in its application. Some of the pros and cons we will be discussing for IGBT. So IGBT advantage, it has simple voltage control operation, high input impedance, high current density, good overload capability, wide safe operating area, available for high voltages, cost effective for medium power, mature and reliable technology. The limitations are, it is limited by switching frequency. There is a tail current which is causing the turn-off delay. No reverse conduction is there. Temperature dependent, latch-up possibility is there, gate voltage sensitivity, and high voltage drop than MOSFET at low current. So compared to MOSFET, you will be having the voltage drop which is higher. So what is the key takeaway? So IGBT is excellent for medium power, medium frequency application with simple drive and high power capability are needed. So such type of applications we prefer the IGBT. Important design consideration you have to do, like in design, protection circuit should be proper, thermal management has to be done, and there should be gate drive design. So protection circuit, you need to use gate protection, over current protection, over voltage protection. So gate protection is done by linear diode, range will be 15 volt rating. Over current protection can be done by current sensing and soft turn off. Over voltage protection can be done with the help of snubber circuit. Thermal management, where the junction temperature should be less than 150 degrees centigrade. So heat sink has to be designed properly. Thermal interface materials has to be there and temperature need to be monitored. Gate drive design, you need isolated power supply, appropriate gate resistance, short connection path, and EMI consideration has to be there, which is electromagnetic interference. Now we will compare all the devices, IGBT, MOSFET and BJT. So this is left to be discussed the thyristor. In the next lecture, we will discuss this. So if you see the drive power, the highest is basically the BJT and IGBT and MOSFET are low. Switching speed is fast for MOSFET and medium for IGBT. On-state loss, if you see, then it is high in MOSFET, low in BJT and medium in IGBT. Voltage rating, current rating, if you see, it is high in case of IGBT, which is preferable. Control, if you see, then full control is there for all the devices. Cost, if you talk about, then the cost is medium in case of IGBT, but low in case of MOSFET and BJT. So where it is best application, we have to go it. So you need to use medium power, go for IGBT, high frequency, go for MOSFET, linear application if you require, then go for BJT. Thyristors, again, will be discussing in very detail. So there we will see this advantage, how the thyristors plays a important role as compared to other power semiconductor device. So selection guide for IGBT is medium power range, kilowatt, moderate frequency less than 100 kilohertz, and high voltage greater than 600 volt. So there we prefer the IGBT. We will revise what we have discussed. So IGBT is basically the combination of MOSFET input and BJT output characteristic. The main advantage is easy to drive, high power capability, and good safe operating area. Main limitation is because of the tail current, which is limiting the switching frequency. Application: motor drives, UPS, welding, and electric vehicles. You need protection devices like the gate overcurrent and overvoltage protection. And parasitic thyristors plays a very important role, and it has to be prevented from latching. These thyristors are best for medium power, medium frequency applications, and gate drive circuits is required in the on state having a voltage of plus 15 volt and minus 8 volt in the off state for proper isolation. So this was the summary of the IGBT power semiconductor devices. So we have covered the BJT, MOSFET, and IGBT. In the next lecture, we are going to focus on the thyristors, its structure, operation, and principle. Thank you for me.